Across the living world, plants build their bodies from long sugar chains. One of the most abundant of these hidden chains is Xylan. It lies tucked inside grasses, grains, hardwoods, reeds, and farm residues. Xylan does not stand alone. It braces walls around cellulose fibers. Together, these fibers make stems bend, trunks stand, and husks endure. For people, that strength has always been both a gift and an obstacle. A wheat straw field can hold food, paper, fuel, bedding, and soil. Yet much of its usefulness remains locked inside tangled plant walls. The lock is not metal, it is architecture on a molecular scale. Xylan winds like a branching vine around tougher cellulose cables. Water alone cannot loosen this woven shelter quickly, completely, or cleanly. Fire can break it, and harsh chemistry can force it apart. But nature learned a quieter way, long before factories or laboratories existed. In forest litter, fungi send fine threads through fallen leaves. Their enzymes taste the wall, snipping one hidden bond at a time. In termite guts, microscopic partners turn dry wood into daily food. In ruminant bellies, microbes unlock grasses during slow, patient digestion. Even bacteria in compost heaps join the same ancient recycling work. Among their tools is Xylanase, the enzyme that opens Xylan. It does not crush the plant wall, it unfastens selected links. The first clues came from 19th-century studies of plant carbohydrates. Researchers boiled plant gums, weighed residues, and searched for unfamiliar sugars. Wood yielded xylose, a small sugar pointing back to a larger material. In 1891, Ernst Schulze described hemicellulose as part of plant walls. Xylan emerged as one major hemicellulose, especially rich in hardwoods and straw. Those chemists saw the locked substance before they knew its biological key. Soon, microbiologists noticed molds and soil organisms could make Xylan disappear. By the early 20th century, Xylan degradation became a laboratory question. Cultures growing on plant fiber hinted at catalysts working outside the cells. After mid-century, enzyme research finally gave Xylanase a clearer shape. Fungal and bacterial xylanases were separated, compared, and given systematic names. Scientists learned that not one xylanase exists, but many related forms. Some came from common molds in soil, others from heat-loving bacteria. Each reflected the habitat where its microbe had evolved and survived. The industrial origin story gathered strength in pulp and paper mills. During the late 1980s, researchers tested Xylanase before pulp bleaching. Their aim was not to dissolve paper, but to free trapped lignin. A gentle Xylan cut could open pathways for cleaner downstream bleaching. Mill trials in several regions showed enzymes could reduce harsher bleaching demands. Xylanase became an early emblem of industrial biotechnology in everyday materials. Its usefulness grew because the enzyme was specific, not forceful. To understand its action, imagine Xylan as a beaded branching strand. The enzyme settles against the chain with a pocket shaped by evolution. A water molecule is guided into position, ready to part a bond. One cut becomes two shorter pieces, easier for living cells to use. The enzyme releases them and returns, unchanged, to another stretch. Side branches on Xylan complicate the path, like knots on twine. So nature often pairs Xylanase with helper enzymes nearby. Together they dismantle plant matter without smoke, flames, or strong acids. This quiet chemistry now appears in many familiar places, often unnoticed by us. In baking, Xylanase can improve dough handling, loaf volume, and crumb softness. It helps release water held within flour's complex fiber network during mixing. In animal nutrition, it helps grains yield more accessible nourishment from fibrous feed. In brewing and plant-based drinks, it can support filtration and smoother flow during production. In fruit processing, it helps clarify juices trapped by plant fibers during pressing. In textiles, it can support cleaner preparation of natural fibers before dyeing and finishing. In pulp mills, it still helps make paper with gentler chemistry and fewer burdens. In biorefineries, Xylanase helps turn agricultural leftovers into useful sugars for further fermentation. Those sugars can become materials, fermentation products, and other renewable building blocks for new products. The same principle connects compost, cattle, bakeries, and paper machines across living systems. A bond is opened, and a stubborn resource becomes more available with less violence. Xylanase reminds us that abundance is not the same as access in green life. The planet grows vast stores of Xylan with every green season on fields and forests. Much of it returns to soil through patient microbial work before new roots drink. Some of it can help replace wasteful chemistry and fossil carbon through careful processes. Learning to unlock it gently is a lesson from fungi and microbes shaped by evolution. The lesson asks industry to listen more closely to decay and borrow its patience. In decay, nature shows renewal instead of simple ending after every falling leaf. Xylanase carries that message from leaf litter to factories that may serve tomorrow. Its long story points toward cleaner materials and quieter transformations for generations ahead. Enzymes Bio is run by people who believe enzymes are the future of clean industry. So we built one platform for startups, labs, and makers to source them without the usual hassle. Gentle on the planet, built for what's next. Visit enzymes.bio.